Okay, so then the question is, once you're actually trying to use this algorithm in practice, there are several choices you need to make. We talked about choosing different values of k. We talked about choosing different distance metrics. And the question becomes, how do you actually make these choices for your problem and for your data? So these choices of things like k and the distance metric, we call hyperparameters because they are not necessarily learned from the training data. Instead, these are choices about your algorithm that you make ahead of time, and there's no way to learn them directly from the data. So the question is, how do you set these things in practice? And they turn out to be very problem dependent. And the simple thing that most people do is simply try different values of hyperparameters for your data and for your problem and figure out which one works best. So the question is where L1 distance might be preferable to using L2 distance. I think it's mainly problem dependent. It's sort of difficult to say in which cases you think one might be better than the other. But I think that because L1 has this sort of coordinate dependency, depending on the coordinate, it actually depends on the coordinate system of your data. If you sort of know that you have a vector and maybe the individual elements of the vector have meaning, like maybe you're classifying employees for some reason, and then the different elements of that vector correspond to different features or aspects of an employee, like their salary or the number of years they've been working at the company or something like that. So I think when your individual elements actually have some meaning is where I think maybe using L1 might make a little bit more sense. But in general, again, this is a hyperparameter, and it really depends on your problem and your data. So the best answer is just to try them both and see what works better. So then the question, I mean, even this idea of trying out different values of hyperparameters and seeing what works best, there are many different choices here. What exactly does it mean to try hyperparameters and see what works best? Well, the first idea you might think of is simply choosing the hyperparameters that give you the best accuracy or best performance on your training data. This is actually a really terrible idea. Like, you should never do this. In the concrete case of the nearest neighbor classifier, for example, if we set k equals 1, we will always classify the training data perfectly. So if we use this strategy, we'll always pick k equals 1. But as we saw from the examples earlier, in practice, it seems that setting k equals to larger values might cause us to misclassify some of the training data, but in fact lead to better performance on points that were not in the training data. And ultimately, in machine learning, we don't care about fitting the training data. We really care about how our classifier or how our method will perform on unseen data after training. So this is a terrible idea. Don't do this. So another idea that you might think of is maybe we'll take our full data set and we'll split it into some training data and some test data. And now I'll try training my algorithm with different choices of hyperparameters on the training data, and then I'll go and apply that trained classifier on the test data, and now I will pick the set of hyperparameters that cause me to perform best on the test data. This seems like maybe a more reasonable strategy, but in fact, this is also a terrible idea, and you should never do this. Because again, the point of machine learning systems is that we want to know how our algorithm will perform. So the point of the test set is to give us some estimate of how our method will do on unseen data that's sort of coming out from the wild. And if we use this strategy of training many different algorithms with different hyperparameters, and then selecting the one which does the best on the test data, then it's possible that we may have just picked the right set of hyperparameters that caused our algorithm to work quite well on this testing set. But now our performance on this test set will no longer be representative of our performance on new unseen data. So again, you should not do this. This is a bad idea. You'll get in trouble if you do this. What is much more common is to actually split your data into 3 different sets. You'll partition most of your data into a training set, and then you'll create a validation set and a test set. And now what we typically do is go and train our algorithm with many different choices of hyperparameters on the training set, evaluate on the validation set, and now pick the set of hyperparameters which performs best on the validation set. And now, after you've done all your development, after you've done all your debugging, after you've done everything, then you take that best performing classifier on the validation set and run it once on the test set. And now that's the number that goes into your paper. That's the number that goes into your report. That's the number that actually is telling you how your algorithm is doing on unseen data. And this is actually really, really important that you keep a very strict separation between the validation data and the test data. So for example, when we're working on research papers, we typically only touch the test set at the very last minute. So when I'm writing papers, I tend to only touch the test set for my problem in maybe the week before the deadline or so to really ensure that we're not being dishonest here and we're not reporting a number which is unfair. So this is actually super, super important, and you want to make sure to keep your test data quite under control. So another strategy for setting hyperparameters is called cross-validation. And this is used a little bit more commonly for small data sets, not used so much in deep learning. So here the idea is that we're going to take our test data, or we're going to take our data set, as usual, hold out some test set to use at the very end. And now for the rest of the data, rather than splitting it into a single training and validation partition, instead we can split our training data into many different folds. And now, in this way, we kind of cycle through choosing which fold is going to be the validation set. So now, in this example, we're using 5-fold cross-validation. So you would train your algorithm with one set of hyperparameters on the first 4 folds, evaluate the performance on fold 4, and now go and retrain your algorithm on folds 1, 2, 3, and 5, evaluate on fold 4, and sort of cycle through all the different folds. And when you do it this way, you get much higher confidence about which hyperparameters are going to perform more robustly. So this is kind of the gold standard to use. But in practice, in deep learning, when we're training large models and training is very computationally expensive, this doesn't get used too much in practice. So the question is a little bit more concretely, what's the difference between the training and the validation set? So if you think about the k-nearest neighbor classifier, then the training set is this set of images with labels where we memorize the labels. And now to classify an image, we're going to take the image and compare it to each element in the training data, and then transfer the label from the nearest training point. So now what we're going to do with the validations, so now our algorithm will memorize everything in the training set, and now we'll take each element of the validation set and compare it to each element in the training data, and then use this to determine what is the accuracy of our classifier when it's applied on the validation set. So this is kind of the distinction between training and validation, where your algorithm is able to see the labels of the training set, but for the validation set, your algorithm doesn't have direct access to the labels. We only use the labels of the validation set to check how well our algorithm is doing. The question is whether the test set, is it possible that the test set might not be representative of data out there in the wild? And this definitely can be a problem in practice. The underlying statistical assumption here is that your data are all independently and identically distributed, so that all of your data points should be sort of drawn from the same underlying probability distribution. Of course, in practice, this might not always be the case, and you definitely can run into cases where the test set might not be super representative of what you see in the wild. So this is kind of a problem that dataset creators and dataset curators need to think about. But when I'm creating datasets, for example, one thing I do is I'll go and collect a whole bunch of data all at once, using the exact same methodology for collecting the data. And then afterwards, you go and partition it randomly between train and test. One thing that can screw you up here is maybe if you're collecting data over time, and you make the earlier data that you collect first be the training data, and the later data that you collect be the test data, then you actually might run into this kind of shift that could cause problems. But as long as this partition is random among your entire set of data points, then that's how we sort of try to alleviate this problem in practice. So then once you've gone through this cross-validation procedure, then you end up with graphs that look something like this. So here on the x-axis, we are showing the value of k for a k-nearest neighbor classifier on some problem. And now on the y-axis, we are showing what is the accuracy of our classifier on some data set for different values of k. And you can see that in this case, we've done 5-fold cross-validation over the data. So for each value of k, we have 5 different examples of how well this algorithm is doing. And actually, sort of going back to the question about having some test sets that are better or worse for your algorithm, this is sort of, using k-fold cross-validation is maybe one way to help quantify that a little bit. And in that, we can kind of see the variance of how this algorithm performs on different of the validation folds. And that gives you some sense of not just what is the best, but also what is the distribution of that performance. So whenever you're training machine learning models, you end up making plots like this, where that show you what is your accuracy or your performance as a function of your hyperparameters. And then you want to go and pick the model or the set of hyperparameters at the end of the day that performs the best on the validation set. So here we see that maybe about k equals 7 probably works about best for this problem. So one thing that is, so k nearest neighbor classifiers on images are actually almost never used in practice because they're just with all of these problems that we've talked about. So one problem is that it's very slow at test time, which is kind of the reverse of what we want, which we talked about earlier. Another problem is that these things like Euclidean distance or L1 distance are really not a very good way to measure distances between images. These sort of vectorial distance functions do not correspond very well to perceptual similarity between images, how you perceive differences between images. So in this example, we've constructed, there's this image on the left of a girl, and then 3 different distorted images on the right, where we've blocked out her mouth, we've actually shifted down by a couple pixels, or tinted the entire image blue. And actually, if you compute the Euclidean distance between the original and the boxed, the original and the shuffled, and the original and the tinted, they all have the same L2 distance, which is maybe not so good because it sort of gives you the sense that the L2 distance is really not doing a very good job at capturing these perceptual differences between images. Another sort of problem with the k-nearest neighbor classifier has to do with something we call the curse of dimensionality. So if you recall back this viewpoint we had of the k-nearest neighbor classifier, it's sort of dropping paint around each of the training data points and using that to sort of partition the space. So that means that if we expect the k-nearest neighbor classifier to work well, we kind of need our training examples to cover the space quite densely. Otherwise, our nearest neighbors could actually be quite far away and might not actually be very similar to our testing points. So the problem is that actually densely covering the space means that we need a number of training examples, which is exponential in the dimension of the problem. So this is very bad. Exponential growth is always bad, and you're never going to get enough. Basically, you're never going to get enough images to densely cover this space of pixels in this high-dimensional space. So that's maybe another thing to keep in mind when you're thinking about using k-nearest neighbor. So kind of the summary is that we're using k-nearest neighbor to introduce this idea of image classification. We have a training set of images and labels, and then we use that to predict these labels on the test set. Oh, sorry, the question is what was going on with this picture? What are the green and blue dots? So here, this was maybe we have some training samples which are represented by points, and the color of the dot maybe represents the category of the point of this training sample. So if we're in 1 dimension, then you maybe only need 4 training samples to kind of densely cover the space. But if we move to 2 dimensions, then we now need 4 times 4 is 16 training examples to densely cover this space. And if we move to 3, 4, 5, many more dimensions, the number of training examples that we need to densely cover the space grows exponentially with the dimension. So this is kind of giving you this sense that maybe in 2 dimensions, we might have this kind of funny curved shape, or you might have sort of arbitrary manifolds of labels in different dimensional spaces. And the only way that because the k-nearest neighbor algorithm doesn't really make any assumptions about these underlying manifolds, the only way it can perform properly is if it has quite a dense sample of training points to work with. Yeah, so the question is, why do these images have the same L2 distance? And the answer is that I carefully constructed them to have the same L2 distance. But it's just giving you this sense that the L2 distance is not a very good measure of similarity between images. And these images are actually all different from each other in quite disparate ways. But if you're using KNN, then the only thing you have to measure distance between images is this single distance metric. And this kind of gives you an example where that distance metric is actually not capturing the full description of distance or difference between images. But yes, in this case, I just sort of carefully constructed these translations and these offsets to match exactly. The question is whether or not it's common in real-world cases to go back and retrain on the entire data set once you've found those best hyperparameters. So people do sometimes do this in practice. But it's somewhat a matter of taste. If you're like really rushing for that deadline and you really got to get this model out the door, then if it takes a long time to retrain the model on the whole data set, then maybe you won't do it. But if you have a little bit more time to spare and a little bit more compute to spare, and you want to squeeze out maybe that extra 1% of performance, then that is a trick you can use. So moving on from, so we kind of saw that k-nearest neighbor has a lot of the nice properties of machine learning algorithms, but in practice, it's not so great and really not used very much in images. So the next thing I'd like to talk about is linear classification. And linear classification is, again, quite a simple learning algorithm, but this will become super important and help us build up to whole neural networks and whole convolutional networks. So one analogy people often talk about when working with neural networks is we think of them as being kind of like Lego blocks, that you can have different kinds of components of neural networks, and you can stick these components together to build these large different towers of convolutional networks. And kind of one of the most basic building blocks that we'll see in different types of deep learning applications is this linear classifier. So I think it's actually really important to have a good understanding of what's happening with linear classification, because this will end up generalizing quite nicely to whole neural networks. So another example of kind of this modular nature of neural networks comes from some research in our own lab on image captioning, just as a little bit of a preview. So here the setup is that we want to input an image and then output a descriptive sentence describing the image. And the way this kind of works is that we have one convolutional neural network that's looking at the image and a recurrent neural network that knows about language. And we can kind of just stick these two pieces together like Lego blocks and train the whole thing together and end up with a pretty cool system that can do some non-trivial things. And we'll work through the details of this model as we go forward in the class. But this just gives you the sense that these deep neural networks are kind of like Legos, and this linear classifier is kind of like the most basic building block of these giant networks. But that's a little bit too exciting for lecture 2, so we have to go back to CIFAR 10 for the moment. So recall that CIFAR 10 has these 50,000 training examples. Each image is 32 by 32 pixels and 3 color channels. So now we're going to take a bit of, in linear classification, we're going to take a bit of a different approach from k-nearest neighbor. So the linear classifier is one of the simplest examples of what we call a parametric model. So now, our parametric model actually has two different components. It's going to take in this image, maybe of a cat on the left, and this that we usually write as x for our input data, and also a set of parameters or weights, which is usually called w, also sometimes theta, depending on the literature. And now we're going to write down some function which takes in both the data x and the parameters w, and this will spit out now 10 numbers describing what are the scores corresponding to each of those 10 categories in CIFAR 10, with the interpretation that larger scores, like the larger score for cat, indicates a larger probability of that input x being cat. Oh, so the question is, what is the 3? The 3 in this example corresponds to the 3 color channels, red, green, and blue, because we typically work on color images. That's nice information that you don't want to throw away. So what's kind of different about this parametric approach, so in the k-nearest neighbor setup, there was no parameters. Instead, we just sort of keep around the whole training data, the whole training set, and use that at test time. But now in a parametric approach, we're going to summarize our knowledge of the training data and stick all that knowledge into these parameters w. And now at test time, we no longer need the actual training data. We can throw it away. We only need these parameters w at test time. So this allows our models to now be more efficient and actually run on maybe small devices like phones. So kind of the whole story in deep learning is coming up with the right structure for this function f. You can imagine writing down different functional forms for how to combine weights and data in different complex ways, and these could correspond to different network architectures. But the simplest possible example of combining these two things is just maybe to multiply them. And this is a linear classifier. So here our f of xw is just equal to the w times x. Probably the simplest equation you can imagine. So here, if you kind of unpack the dimensions of these things, we recall that our image was maybe 32 by 32 by 3 values. So then this becomes, we're going to take those values and then stretch them out into a long column vector that has 3072 by 1 entries. And now we want to end up with 10 class scores. We want to end up with 10 numbers for this image, giving us the scores for each of the 10 categories, which means that now our matrix W needs to be 10 by 3072. So that once we multiply these two things out, then we'll end up with a single column vector 10 by 1, giving us our 10 class scores. Also, sometimes you'll typically see this is we'll often add a bias term, which will be a constant vector of 10 elements that does not interact with the training data, and instead just gives us some sort of data-independent preferences for some classes over another. So you might imagine that if your data set was unbalanced and had many more cats than dogs, for example, then the bias element corresponding to cat would be higher than the other ones. So if you kind of think about pictorially what this function is doing, we have in this figure, we have an example on the left of a simple image with just a 2 by 2 image, so it has 4 pixels total. So the way that the linear classifier works is that we take this 2 by 2 image, we stretch it out into a column vector with 4 elements. And now in this example, we are just restricting to 3 classes, cat, dog, and ship, because you can't fit 10 on a slide. And now our weight matrix is going to be 4 by 3, so we have 4 pixels and 3 classes. And now, again, we have a 3-element bias vector that it gives us data-independent bias terms for each category. So now we see that the cat score is going to be the inner product between the pixels of our image and this row in the weight matrix added together with this bias term. So when you look at it this way, you can kind of understand linear classification as almost a template matching approach, where each of the rows in this matrix correspond to some template of the image. And now the inner product or dot product between the row of the matrix and the column giving the pixels of the image, computing this dot product kind of gives us a similarity between this template for the class and the pixels of our image. And then this bias just, again, gives you this data-independent scaling offset to each of the classes. So now, from this template matching, if we think about linear classification from this viewpoint of template matching, we can actually take the rows of that weight matrix and unravel them back into images and actually visualize those templates as images. And this gives us some sense of what a linear classifier might actually be doing to try to understand our data. So in this example, we've gone ahead and trained a linear classifier on our images. And now on the bottom, we're visualizing what are those rows in that learned weight matrix corresponding to each of the 10 categories in CFAR 10. And in this way, we kind of get a sense for what's going on in these images. So for example, on the bottom left, we see the template for the plane class kind of consists of this blue blob, this kind of blobby thing in the middle and maybe blue in the background, which gives you the sense that this linear classifier for plane is maybe looking for blue stuff and blobby stuff, and those features are going to cause the classifier to like planes more. Or if we look at this car example, we kind of see that there's a red blobby thing through the middle and a blue blobby thing at the top that maybe is kind of a blurry windshield. But this is a little bit weird. This doesn't really look like a car. No individual car actually looks like this. So the problem is that the linear classifier is only learning one template for each class. So if there's sort of variations in how that class might appear, it's trying to average out all those different variations, all those different appearances, and use just one single template to recognize each of those categories. We can also see this pretty explicitly in the horse classifier. So in the horse classifier, we see green stuff on the bottom because horses are usually on grass. And then if you look carefully, the horse actually seems to have maybe 2 heads, one head on each side. And I've never seen a horse with 2 heads, but the linear classifier is just doing the best that it can because it's only allowed to learn one template per category. And as we move forward into neural networks and more complex models, we'll be able to achieve much better accuracy because they no longer have this restriction of just learning a single template per category. So if you think about what another viewpoint of the linear classifier is to go back to this idea of images as points in a high-dimensional space. And you can imagine that each of our training images, or each of our images, is something like a point in this high-dimensional space. And now the linear classifier is putting in these linear decision boundaries to try to draw linear separation between one category and the rest of the categories. So maybe up on the upper left-hand side, we see these training examples of airplanes. And throughout the process of training, the linear classifier will go and try to draw this blue line to separate out with a single line the airplane class from all the rest of the classes. And it's actually kind of fun if you watch during the training process. These lines will start out randomly and then go and snap into place to try to separate the data properly. But when you think about linear classification in this way, from this like high-dimensional vector point of view, you can start to see, again, what are some of the problems that might come up with linear classification. And it's not too hard to construct examples of data sets where a linear classifier will totally fail. So one example on the left here is that suppose we have a data set of two categories, and these are all maybe somewhat artificial, but maybe our data set has two categories, blue and red. And the blue categories are the number of pixels in the image which are greater than 0 is odd. And anything where the number of pixels greater than 0 is even, we want to classify as the red category. So if you actually go and draw what this what these different decision regions look like in the plane, you can see that our blue class with an odd number of pixels is going to be these two quadrants in the plane, and even will be the opposite two quadrants. So now there's no way that we can draw a single linear line to separate the blue from the red. So this would be an example where a linear classifier would really struggle. And this is maybe not such an artificial thing after all. Instead of counting pixels, maybe we're actually trying to count whether the number of animals or people in an image is odd or even. So this kind of a parity problem of separating odds from evens is something that linear classification really struggles with traditionally. Other problems that other situations where a linear classifier really struggles are multimodal situations. So here on the right, maybe our blue category has these three different islands of where the blue category lives, and then everything else is some other category. So for something like horses, we saw on the previous example, is something where this actually might be happening in practice, where there's maybe one island in the pixel space of horses looking to the left, and another island of horses looking to the right. And now there's no good way to draw a single linear boundary between these two isolated islands of data. So anytime where you have multimodal data, like one class that can appear in different regions of space, is another place where linear classifiers might struggle. So there's kind of a lot of problems with linear classifiers, but it is a super simple algorithm, super nice and easy to interpret and easier to understand.
K-Nearest Neighbor를 웹에서도 실행할 수 있습니다. 아래 주소를 보면 스탠포드에서 제작한 데모가 있습니다. 또한 K값을 비롯한 파라메타를 조절해서 그래프가 바뀌는 것도 관찰할 수 있습니다. K값 혹은 디스턴스 메저는 하이퍼 파라메타라고 하는데 데이터를 통해서 학습되는 것이 아니라 우리가 알고리즘에서 세팅하는 값입니다. 하이퍼 파라메터의 값은 problem dependent, 문제에 따라서 적절한 값이 달라집니다. 어떤 것이 제일 좋은 값인지 여러 가지를 시도해보고 결정해야 됩니다. 첫 번째 아이디어는 데이터에 가장 잘 동작하는 하이퍼 파라메터를 선택하는 것입니다. 이 방법의 문제는 K값이 이를 때 트레이닝 데이터에서 가장 잘 동작한다는 것입니다. 두 번째 아이디어는 데이터를 트레인 데이터와 테스트 데이터로 나누고 테스트 데이터에서 가장 잘 동작하는 것을 하이퍼 파라메터를 선택하는 것입니다. 이 방법의 문제는 하이퍼 파라메터가 테스트 데이터에 맞게 세팅되어 있어서 새로운 데이터에 알고리즘이 어떤 결과를 낼지 알 수 없다는 점입니다. 세 번째 방법은 데이터를 트레인 데이터, 밸리데이션 데이터, 테스트 데이터로 나눠서 하이퍼 파라메터를 밸리데이션 데이터를 통해서 얻고 테스트를 통해서 평가하는 것입니다. 이 방법이 가장 좋은 방법이라고 할 수 있습니다. 네 번째 방법은 크로스 밸리데이션입니다. 데이터를 폴더로 나누고 각 폴더에 대해서 밸리데이션을 구한 뒤 그 결과를 평균 내는 것입니다. 작은 데이터셋에서 이용하지만 데이터량이 풍부한 경우에는 딥러닝에서 자주 사용되지 않습니다. K-Nearest Neighbor는 이미지 분류에서는 사용되지 않습니다. 첫째로 테스트 타임이 너무 느리기 때문입니다. 둘째로 픽셀에 대한 디스턴스 매트릭이 충분한 정보를 제공하지 않기 때문입니다. 그림의 사례를 보면 오리지널 이미지와 이를 변형시킨 3개의 이미지들이 있습니다. 모두 같은 L2 디스턴스를 가지고 있어서 정보에 변별력이 없습니다. 또 다른 이유는 Curse of Dimensionality입니다. 디멘전이 1, 2, 3으로 증가함에 따라서 포인트가 4의 1승, 4의 2승, 4의 3승으로 기하급수적으로 증가하는 것을 알 수 있습니다. 다음은 Linear Classification, 선형 분류입니다. 나중에 뉴럴 네트워크와 컨볼루션 신경망을 배울 때 필요한 기본 개념이기 때문에 잘 익혀두는 것이 필요합니다. 뉴럴 네트워크를 만드는 것은 레고 블록을 조립하는 것과 같습니다. 리니어 클래시파이어는 이 레고 블록들 중 일부를 구성합니다. 왼쪽 그림을 보면 4개의 사진이 있고 이것을 설명하는 문장이 있습니다. 이러한 일들을 해내기 위해서는 좀 더 간단한 오브젝트 디텍션 사례부터 살펴보도록 하겠습니다. 오른쪽 그림에는 CNN 아키텍처를 사용해서 이미지에서 스트로햇이라는 오브젝트를 디텍트한 것을 보여주고 있습니다. 시프라10의 데이터셋의 사례를 회상해보면 에어플레인부터 트럭까지 10개의 클래스가 있었고 5만 개의 트레이닝 이미지와 1만 개의 테스트 이미지들이 있었습니다. 파라메트릭 어프로치에서 인풋 이미지가 32 곱하기 32 곱하기 3의 어레이를 갖고 있으면 이는 3072개의 숫자에 해당이 됩니다. 함수 f는 이미지 x와 파라메타 혹은 웨이트 w를 인풋으로 하여 클래스 스코어를 나타내는 10개의 숫자를 아웃풋으로 제공합니다. 함수 f는 여러 방법으로 구현할 수 있는데 가장 간단한 것은 파라메타와 웨이트를 w 매트릭스로 구현하고 이에 인풋 x를 곱하는 것입니다. 이를 리니어 클래시파이어라고 합니다. 디멘전을 보면 fxw는 10 곱하기 1의 벡터이고 w는 10 곱하기 3072의 매트릭스이며 x는 3072 곱하기 1의 벡터입니다. 여기에 10 곱하기 1의 벡터인 바이어스 b를 더해주면 좀 더 일반화된 리니어 클래시파이어를 얻을 수 있습니다. 다음은 간단한 사례로서 인풋 이미지가 4개의 픽셀을 갖고 있고 cat과 dog과 sheep의 3개의 클래스만 가진 경우입니다. 2x2의 인풋 이미지 픽셀들이 스트레칭 돼서 4x1의 컬럼 벡터 x가 만들어진 것에 주목해 주시기 바랍니다. W 매트릭스와 바이어스 B 벡터는 트레이닝 데이터 러닝을 통해서 학습되는 것입니다. WX 더하기 B를 통해서 cat과 dog과 sheep의 스코어가 만들어졌습니다. 그 결과 dog의 스코어가 가장 크기 때문에 dog로 분류를 합니다. 왼쪽 사진에서 보듯이 이는 잘못된 분류입니다. 따라서 W와 B를 조절해서 에러가 난 만큼 다음번에는 올바른 분류를 할 수 있도록 하는 것이 학습의 기본 메커니즘입니다. 우리는 리니어 클래시파이어가 이러한 데이터셋들에 어떤 일들을 하고 있는지에 대해서 생각해 볼 수 있습니다. 이를 그래프로 나타내 보면 샘플 데이터의 스페이스를 10개의 클래스로 분할한 것으로 생각할 수 있습니다. 다음은 3개 이미지에 대해서 10개 클래스의 스코어를 구한 것입니다. 첫 번째 사례를 보면 cat이 2.9점이 나왔는데 디어나 독의 경우 이보다 높은 점수를 가지고 있어서 좋은 분류라고 할 수가 없습니다. 두 번째 사례의 경우 오토모빌이 6.04로 가장 높은 점수를 받아서 이것은 좋은 분류라고 할 수 있습니다. 프로그의 경우는 마이너스 4.34인데 아홉 번째로 낮은 점수를 받아서 매우 나쁜 분류인 것을 알 수 있습니다.